IQT, where they should be described by coordinate factorization, they show the discrepancies with the theory. So we decided to look into the available giant data and see what happens. So this is one example of this, the oldest example of the available set of data. These data are at low QT, they are expected to be described by transverse momentum resummation and mainly by non-perturbative effects. Indeed, this is where the TMD fits are done. So this is one example of an old fit, the Drell-Yan fit. At some point, if you look at the high QT part of the spectrum, you expect the fixed order to be applied, to be reliable. But it happened that we looked into the literature, we cannot find really many studies on it. Only some studies from the 70s when the partner solution functions were not so well known. Okay, so our question is, can we describe the data here?
Why have you chosen this set of data?
I know it does as an introduction because it has a beautiful shape. Because it has this shape, it shows the shape, Gaussian shape at low QT and some flattening at high QT because it reaches very high QT. That's the reason. But it's very old. It's not such a.
It's very infamous.
Infamous, yeah.
Because
I agree.
They just provide the drawing and not the numbers.
Yeah.
So
yeah.
You fit some numbers extracted from the picture.
It's beautiful.
So,
someone used it. I think some reason people used it anyway. Okay. Okay. So I will briefly talk about the W+Y prescription because also another reason because I chose this data is because here is the only example of the low energy data where you find the entire QT spectrum. You cannot see anything. You can find the entire QT spectrum described by the theory. Okay, this is an example. The only example you have is on a paper from the 90s where they do W+Y, and they seem to be able to describe the whole spectrum. But here comes an issue because at some point here, W+Y shouldn't be the most precise thing to do. We should do fixed order. I say this because I'm applying this rule, which I like to call the Arnold Kauffman's rule from this famous paper. Okay, the rule that is often adopted is that when your W term gets negative, the error you make doing W+Y is bigger than the error you would make using only the fixed order. It's because the cancellation is not more accurate. By the way, it is interesting to me to think of this also when we are looking at cities, because usually when people try to fit cities data, in reality they use the W up to QT equal Q. But if you stick to if you're looking if you want, it's not accurate because if you look at how the asymptotic term goes, it goes negative much before. So it means that you are using the W in a region where even the W+Y shouldn't be accurate. Just a brief comment on cities. Now, we decided to look at the point where the expansion of the summation goes negative. Okay, this should be a good indication of the point where you should switch to the coordinate factorization. So as here you see the asymptotic and fixed order at order alpha s square. Okay, and you see that we understood the data. Okay, this is an old set of data, not so precise. So the next step is to look at all the available Drell-Yan data and see what's the general trend. So it's worth spending a few words about the data that are available, because they are few and they often have issues. So here are if you look at the most recent papers and T&D papers, here are the data that you will find. Okay, there is the famous one, and the other two data from Fermilab. One thing to say is that just this one is actually used also in PDF feeds besides T&D feeds. And also this one has been abandoned in the most recent feeds. But if you look back in time, you will find more data. So for instance, you will find the pion-Drell-Yan data, which Arnold will discuss. And also a very rich set of data which are actually used in PDF feeds, but not in T&D feeds, since they are not on a paper, not published. Okay, so these are the data that we consider. As Christine has mentioned last time, there are also interesting case of ghost data. So this data from from proton, deuteron, and p-bar tungsten, which somehow disappeared from theoretical studies. So in the case of E772, because the first publication contained errors, but then some years later it was an erratum was published, but it seems that people did not consider the erratum. And in case of p-bar W, I cannot tell you why somehow it disappeared. Okay, so let's look at the comparison theory against data. So here you can see against the comparison with the most recent data, the new data. This is the alpha square calculation, NLO, with the bearing of resummation, renormalization and factorization scales around 1/2 Q and 2Q. And you see here is the region we should expect it to be reliable, and the K factor is big, can go up to 6. So the trend is general among all the sets that we have considered. So what can be the explanation? One could think, well, when you look at the analog cross-section and faculty, the gluon channel is important, for instance, and you're sensitive to the gluon distribution at particularly high values of X. So one can imagine maybe there is the gluon distribution is not so well known at the medium to high X, but this seems to be not the case, because if you look at the calculation by considering the PDF uncertainty, this is from CT14. You see that the uncertainty is quite small. You can do the same exercise with the dynamic PDF sets. So I took all the available all the replicas from the PDF sets, and they did not move far from here. So it seems to doesn't seem to be that problem. Also, another thing to notice is that here there is a scale variation at LO and NLO, and they are, you see the bands in this region, which is the region we are considering, they are quite well contained one inside the other, so it doesn't signal a failure of your expansion. Okay, here is just to show that the trend is similar for the other experiment, INT-18-3, which is a lower square root of S. nothing here. Usually bigger uncertainties, however.
Oh, sorry to interrupt. Do you consider at all W term in this study?
No, we do not. So in this for this set of data, you can look at the W term from the fit studies. Okay, and the region where the fit are done is this region. Okay, so in Piacenza the W term dies around this point where not exactly where the asymptotic dies, but in this region. Okay, so from here on, we are looking at this part of the spectrum.
For the formalism to work flawlessly, in principle, we need to have matching of the asymptotic, where the asymptotic becomes negative and where the W term becomes negative too. So if there is this big mismatch,
yeah,
then it's an indication of some fine-tuning that we have to do that. So just choosing where the asymptotic becomes negative, it's a choice, of course. And then you say, now I have to start my flow calculation. On the other hand, you should also think what is happening if you go for value calculation. I don't know, might be not relevant in this case.
Yeah, I agree that it's a choice, but okay, if you go from the other side, I looked at where the W reaches. It's not very far from here. Okay, they do not match. We know there's a problem with matching, but I think it's fair to say that here at least there should be a fixed order.
Yeah, I mean, it could be completely agnostic on the way of matching. You could just argue we come from the large QT side, we do fixed order calculation, and then we, go see how far it carries us. Because of course, at low QT, it will diverge and it will, describe the data, and somewhere above it will start to make sense.
Yeah, one possible matching, a little bit smoother than this, is when the W, in the sense, you cancel the asymptotic. So that when, yeah, that's a place you get, because W is always larger than the asymptotic in the small QT. Eventually getting closer and closer to the point there. When they are sort of equal, then the perturbed take home.
Then the next slide is for Aurora. I wanted to show you. I tried to do the same thing with the pion-nucleus Drell-Yan, as you wanted to know. And here the trend is quite similar. However, the errors touch with the are not so composite. Okay, I don't have the asymptotic here. If you want, we can think of it. Okay. So one can think, okay, these experiments are all experiments at low square root of S. So there may be an important effect of threshold resummatio, which is essentially which is important when where your partons have just enough energy to produce your final state, so they can't be on the photon. And so it is the resummation in this YT variable. Okay, so the Bernard took care of it. So this is the result of next to leading log threshold resummation. And let's start from the lowest energy experiment. So you see here the impact of resummation is okay. It's quite important. It's outside of the uncertainty band, of the NLO uncertainty band. In any case, as you go up with the square root of S, so you see here, as you go up with square root of S, the impact reduces until you go to the highest energy experiment, where the impact is this. So the difference between NLO is here is the red curve, and the resummation is the green curve, so the impact is very, very reduced. So it seems to give, okay, it's interesting because we've seen that in some cases you cannot ignore threshold effects, but it doesn't seem to give the whole answer.
I have a question there. I mean, that is due to the fact there is no error band, so there's some curve.
Okay, okay. In this case, we have then gave me the error band, but I didn't put here because it's really, you can see, you can distinguish on the result is not correct. So the error when I saw it.
It's relatively relatively narrow. Certainly narrow, I think, than the distance to the low error band.
I cannot understand why.
I mean, it should be really. I mean, of course, it doesn't always happen that way. But
it should become
yeah.
smaller, yeah, but typically
Yeah.
it's not so
I think
plastic.
Yeah, I know. But I think Drell-Yan is usually very well behaved on many kinds of aspects. So, you know, what we saw in the electron schedule was much worse than Drell-Yan for some reason always works better.
Okay. Then I think we can take inspiration from other cases where similar problems have shown up. So one example is the pion production. Here you see some plots for PP going to P0, quite old plots, but also in this case you have a discrepancy at quite low PT and the low energy, which didn't seem to be solved by resummation. These are quite old sets of fragmentation functions, but nowadays the situation with new sets is not improved. And another similar case is the prompt photon cross section. In this case, the problems were seen also in a Fermi-Lab experiment, but the situation is somehow inconclusive because it seems that this is almost the only experiment which shows such a huge discrepancy. So what was one thing that was done in this case is to try to solve the discrepancy is the intrinsic KT smearing, which is a phenomenological model to try to approximate some power correction to the section. So what is it? So you take your collinear factorization formula. You allow your incoming photons to have a small initial transverse momentum. So your convolution becomes a convolution also including the integral over the initial KT. And by doing this, the Mandelstam invariance and the partonic cross section will be modified. And so you have also to take in consideration to modify the initial parton flux. That's why you have this factor. As I said, this is quite an old model. It is a long history from the 80s. Also, the original idea by Sievers is formulated in this model, and also a lot of work concerning the Sievers and some Sievers in pion production from Andalese and Murgia and many others. One important thing to keep in mind is when you do this model, the initial KT of your parton is not just non-perturbative KT, but is usually you take into consideration also the summation of soft Coulombs, but then you also have a Coulombs emission here, and so you're actually doing double counting. So you must handle with care this kind of models. Okay, let's look into the details. So we try to adopt this model also in Drell-Yan for the first time, and to see what are the effects. So we took the parton to remain on shell, and also we kept the usual definition of the X variable. So this is the choice we made for the parton momentum. And one thing to pay attention is that with choice, very weird things can happen. If you exaggerate with the chances of initial chances momentum, okay, your torque energy may exceed the total energy, or even the torque may reverse direction. And so when people does this kind of model, they usually take this as a bound for KT. We think it's better to stay far from this bound, since it means that you are already far from the approximation of the factorization. So we checked when doing the calculation, we checked that our cutoff on KT is actually lower than this, and that our results do not depend much on the cutoff.
What do you mean to stay far from the bounds? What does it mean?
Okay, I mean, if you
In practice,
in practice is if you take a square root of s like 40, like is in our experiments, so these bounds are several GVs. So
they depend on x.
Depend on
Sometimes it's
x.
zero. Sometimes the KT
yes,
cannot be in. So,
yes, but you also have an x mean. When you do the integration here, you have an x mean. So it's not zero. The x mean.
I think what is relevant is what is the effective value of the T for your hot power T-channel exchange.
Yeah.
When you have KT, sometimes you can run into a situation that T close to zero, right? And all the PT you observe come from initial KT.
Mm-hmm.
Now, of course, the hot part is no longer hot part.
Yeah.
So with this kind of bound, you can control it. How you choose the bound will determine what the range of the T you have. If the range of the T becomes so small, which of course is good, can boost up your cross section. On the other hand, it's not quite perturbed.
Yeah.
So what is exactly the value or range of T you have with this one?
Yeah. Okay. I will show you. I will tell you the merits later. Okay. Yeah. Indeed, as you were saying, another important thing is to make sure that your T hat does not get too small, because it must be a hard part. One won't be hard. So, okay, there is no general consensus on how to select a specific KT max. So I'm going to show you what we did. Okay. First of all, what did we use for the initial chances momentum distribution? So we took the chances momentum distribution from the Papier fit. Here I show you this distribution at Q of the experiment we are looking at. So you see this is the intrinsic KT, and here when you apply evolution, you go down to this curve. The major role is played by the non-perturbative evolution, actually. So the logs are really a small part here. So one thing is that, as I was saying, we want to make sure that our calculation do not depend on the cutoff we choose for KT max. And if you use this form for your KT distribution, this becomes an issue. Why? Because these certain distributions from the fit, the blue curve here, have along a high tail at high KT, which is actually out of the range of TND. So this tail does not actually have a physical meaning.
Sorry, is this the sum of two functions?
Okay, this blue curve is the result of evolution, so it's not just.
Oh, sorry, as an input, you said
we take the sum of the two Gaussians, which is the intrinsic chances momentum, which is in this case the blue curve. Okay, but then we also add the non-perturbative evolution, so we are here with the green curve, and the perturbative evolution, which is here. So it's all the contributions together. Okay, as I was saying, if you use this distribution, you have this high tail, and then your results do depend on the KT max cutoff, but they don't depend on this because of any physical reason, because here your distribution does not have any meaning. So we chose to approximate our result with the usual Gaussian in the end. We wanted to be clever, but then we ended up doing the usual thing. Okay, it turns out that to approximate your curve, the Gaussian has to be a width of about, say, 1 GB at these kinematics. So, and at the end, what happens? Okay, sorry. To answer your question, you somehow have some lower limit on KT max if you adopt this choice, because you cannot take KT max to be, let's say, below 1 GB, but we checked what are the different results you get by varying KT max, let's say, from 1 GB to 5 GB, and actually the results do not change after 1.5 GB. Okay, so let's say that's our value of KT max.
Just a question of t value or u value.
Okay, the t value depends on the QT.
Yeah.
Okay, and so that's why here is the smeared result against the leading order one. Okay, so by looking at the t values numerically, I can say we do not trust the results here below, let's say, 3 GB. But we can rely on the results here.
But also the KT average depends on the S.
Yeah.
So you choose the one value for all the data, or just how you choose?
No, okay, now I'm just showing one example with one given value of S and Q. So this is the distribution I chose for that given S and Q.
Based on the feedback.
Taken from the TND fit. So this is the result of this meeting. So you can see this is okay. It's not a huge effect.
I mean, you become independent of this cut because you have a Gaussian. But couldn't you have taken something else in the Gaussian?
Yeah,
and therefore wouldn't you have to add substantial systematic uncertainty?
Okay, we tried also the different distribution with a different tail. But I would say then the KT max dependence is not a physical meaning because what's it? I mean, you are going in a region where your T hat is very small, and so your hardware perception is not reliable.
Yeah, that's why it enters only the error. And not,
sorry?
That's why it would only enter the error. I mean, basically, you don't know what you have. I mean, you try to quantify the dependence on this upper cut, but if I understand correctly, you try to quantify it with an ad hoc assumption. or not.
Yeah, so here the idea is to estimate, let's say, an upper bound of what this smearing could be. We imagine that in reality, because this takes KT square 0.81, which is the result of the feedback plus also the evolution. So in reality, maybe you should consider only the intrinsic part. So this is a kind of upper bound of what can happen, we believe. So in reality, your tail or your distribution will be even narrower than this. And then the dependence on the KT max should not be so important.
How do you know that this is an upper bound? I mean, Gaussians decay very fast, yeah? And so this is an assumption which reduces decay. So
I think I agree with you. It's Gauss. From the formalism you have, you certainly have the region when the T is very small, but because the choice of Gaussian, those regions have very small contribution to the overall cross sections. And then back to the question that Andrew asked, say what shape of the Gaussian determine the error, how much trouble you have. But that relates to that width. That width actually depends on the radius and the pitch. It's how much face space you have to shower. So that how you control what's your predictive power? Say I fix this data, say A66, Now try to apply the formalism to the data at another collision energies, and how that will change your uncertainties. So that part is a predictive power part. I'm not sure. In some sense, I agree with Andrew. How do you control that?
Okay, so the point is how far we can get within the formula. So if it is true that you can put a tail which increases things dramatically, then it means that you are out of the applicability of the formalism anyway. So in a sense, this is trying to save as much as possible all the formalism, stretching it a bit with the kitty smearing, but without really violating all the assumptions.
Okay, that's it. I'm done with my talk. Okay, so
We already had several questions, but if you want to add
Just
something
about
more.
the fire. So you also use to get fire times the Gaussian, and you don't get the shape.
no, no, we didn't look at the OPT. It's just the collinear, the fixed order, collinear factorization result. Okay.
Oh yeah, okay. So we have to check that.
Okay.
What fire medium?
Okay, we use the all the set. The
Well,
but
no, but
MS that one.
it's not
Yes,
included.
MLS.
But they have to land data, so
No, but the QE integrated. That.
yeah, not that,
Yeah.
but it's the same sense.
Not what I do. Not the
There
same
must be a
thing.
strong correlation.
So if the gluon distribution were true, that data, it might be that you will get much better activity.
Yeah, but it's so strange because ion pairs repeat from the same set.
But the EQ integrate and
They
HO
integrated it,
does
I
not
think.
depend on the glue, right? That cross section depends on the glue, EP by EP. So it might be that it is needed to the higher get this aspect. People claiming it doesn't work at all.
Yeah.
But I think the issue is generic. I mean, we have, it's not just the, you might click around with the pylon, but the PP is what he points out, right? I mean, you're just below, significantly below the data IQT. Whether you try to press it with smearing or with threshold corrections, it just doesn't change anything, right? And so it just is a big issue, I think, because that's a region where really things should work. And I think it ties well into your cities result that you want to show. And I don't think we understand this problem presently, right? I mean, we're struggling with IPT, ion cross sections in PP or whatever, but this is even simpler, right? It's an IQT Drell-Yan cross section, it's large Q, relatively large QT, and that somehow it should work. Right? It's really, I think, an outstanding issue. What he's showing is really that these conventional tools we have for addressing that don't seem to really help us. And we use that kind of stuff a lot for TMD studies, for spin physics, right? And so there's something that needs to be understood.
What about it? That there is like coupler, Houston,
Yeah.
how do you deal with it?
Okay.
And if you can get some answer.
Yeah. So I did with the INT-18-3. Okay. Also with by looking at the PDF uncertainty from INT-18-3. They are still narrow. They're not very larger than this uncertainty, which is for the case of 14%. The CTEC and CTEC.
Because the NCTEC has some very funny behavior if they use actually the neutrino data. So there's quite some discussion in the PDF community whether that is really fully correct.
But in any case, I can say in the case of Drell-Yan, they are not very different from doing a PP calculation. So if you do PP or PCU in university, that's not very different in this case.
Yeah, I would claim on that scale you would not see a difference between.
Really?
Absolutely not. I mean, it's 10% effect we're talking about, so maybe 20%. So this is factors of 5, decision factors.
Oh yeah, okay, fine. You cannot use the factor of 5. I don't think. Yes. Okay.
For your next meeting or the half part, assume you calculate the Fourier factorization.
Yes, absolutely.
Is it possible we can generalize this factorization first just to indicate the subtraction term rather than the normal Fourier? We introduce a subtraction term with KT dependent. Only thing we require is onshore, half time onshore, so we can back that. You introduce a different subtraction scheme and with a KT dependent.
I personally did not understand what you suggest. So can you?
Sure. So when you go, especially for Drell-Yan, you do have a larger scale of the sitting. So then when you calculate next leading order, you have a Fourier derivative from each step. So normally the Fourier factorization approach, you subtract out the PC in the Fourier PDF. So whether it's MSR or whatever scheme you choose, you subtract it. Then you get the next leading order. Now when you apply it, I believe you just change the kinematics. You keep the same half part, except the initial part-time momentum with the KT dependence. So you change the kinematics. So maybe we can generalize these for this low integer fixed Fourier experiment case. Then instead of when I define my half part, I define my half part in a perturbative Feynman diagram atomic cross section, subtract the piece in the PDF, but it's not the collinear part of PDF. With the collinear pole, of course, we need to subtract it, but plus some KT dependence without double cut in your initial lawsuit. So in that case, you might smooth out, when you smooth out the transition from this T channel form,
right,
and also maybe have more systematic way to go beyond the complexity.
Yeah.
Because if you take the normal collinear factorized calculate next leading order beyond, you only hit the trouble with the T channel singularities. So then maybe there's a new way to subtract it, subtract the T dependent PDF contribution. In that case, you will have something smooth